Hello, everyone. So last time we were looking at the concept of continuity. Last time, continuity. So continuity, we said that, intuitively, it means that, the graph of the function has no hole or break. And formally, the function is called continuous if the limit is called continuous at x equals a. If first of all, f of a is defined, meaning that a must be in domain of f, and limit f of x as x approaches to a exists, and the value of the limit must be equal to the f of a, right? So if these conditions hold, if limit f of x as x approaches to a equals f of a, then we call the function continuous. And we define the also continuity on an interval. So let's say on an open interval, half open, half closed interval, and also on a closed interval, we define continuity. And we also saw about some properties of continuity. Properties of continuity for, addition or scalar multiplication. A product, a division of two functions. So we saw the properties for these operations on functions. So for example, if you have two continuous functions, the addition of those two functions will be continuous, or multiplication of two continuous functions continuous. Division also is continuous as long as denominator is non-zero. So another important property that we want to see today, and last time we didn't have time to cover it, is about composition of, I can say continuity of, let me say more properties. Continuity of composition of two functions. So suppose that f of x and g of x are functions such that limit g of x as x approaches to a is equal to L, and suppose that f of x is continuous at L, right? F of x is continuous at L. At x equals L, then we can say that limit f of g of x as x approaches to a exists, and we can say that limit f of g of x, so composition of f and g as x approaches to a, is equal to f of L. So as x gets closer and closer to a, g of x gets very close to L, according to my assumption here. G of x will get very close to L. So f of g of x will get very close to f of L as long as f is continuous at L. So in particular, we can say that if g of x is continuous at A, and f of x. So g of x continuous at A means what? i.e. limit g of x as x approaches to A is equal to g of A and if f of x is continuous at g of A then f of g of x is continuous at x equals A, meaning that limit f of g of x as x approaches to A is equal to f of g of A. You just need to set L equals g of A in the statement above. See, this statement is valid for any L. For any function f, any function g, any point A, and any value L. But now if I set L to be g of A, then limit g of x equals g of A means g is continuous. So we said that in particular, as a special case of this statement, if g is continuous at A, meaning that limit g of x equals g of A, and f is continuous at x equals L, L is g of A. So in particular, if g is continuous at A and f is continuous at g of A, my L value is g of A, then f of g of x, then what can I say about limit f of g of x? Limit f of g of x according to this statement is f of L, but my L right now is g of A, so limit f of g of x can be written as f of g of A. So that's what I wrote here. Limit f of g of x equals f of g of A. But what does that mean? That means the function f of g of x is continuous at x equals A. Because how should I check continuity at x equals A? I have to calculate limit of the function at x equals A and compare it with the value of the function at A. So limit function at A, so limit f of g of x at A is f of g of A, which means the function is continuous at x equals A, because these two values, the value of the limit and the output of the function, these two values are the same, therefore the function is continuous. Okay. So let's look at an example first. Let f of x equals e to the x and g of x equals 2x. So f continuous everywhere. So g, first of all, let me say at any point, let me write it this way, at any point x equals c in R, g of x, first of all, is continuous. Why g of x is continuous? G of x is 2x, which is a polynomial. Polynomials are continuous everywhere. Polynomials are continuous everywhere. Also, f of x equals e to the 2x is continuous. See, I want to look at the composition of f and g, which is e to the 2x. We want to establish that e to the 2x is a continuous function. Well, g of x, which means we want to show f of g is a continuous function. So if I want to do that, first of all, I have to check g of x is continuous at any point, let's say a or c. Then f of x must be continuous at g of a. Then I can say f of g of x is continuous at a. So far we said g of x is continuous at c. Now I have to say that f of x is continuous at g of c. Continuous at g of c. How much is g of c? If g of x is 2x, then g of c will be 2c. Again, because e to the 2x, f of x is e to the x, not e to the 2x. If I say e to the x, continuous at g of c equals 2c, because e to the x is continuous everywhere, as seen last time. So that means f of g of x, which is e to the 2x. F of x is e to the x, g of x is 2x, so f of g of x is e to the 2x, is continuous at x equals c for any real number c. So that means e to the 2x, e to the 2x is continuous on minus infinity to infinity, because this argument is valid for any real number c. So we can say this function e to the 2x is continuous on the whole interval minus infinity to infinity, because for any point c inside this interval, the function f of g of x is continuous. Okay, now one question I want to ask here. In above, we saw that if limit g of x as x approaches to a is equal to L, and f is continuous at L, then limit f of g of x as x approaches to a is equal to f of L. So this is the statement, this is the theorem basically that we saw above. In this course, we are going to mention the statements of theorems, but we are not going to include the proofs in most cases. In most cases, we will not include the proofs of theorems. The proofs of theorems, these theorems you can learn in an analysis course, basic analysis course. You also have it in the college math 225 analysis 1. But for this course, we'll include some proofs, but like for major theorems, mostly no. Some major theorems will prove it, but mostly no. So this theorem, this is a theorem. It says if limit g of x is L and f is continuous at L, then limit f of g of x equals f of L. Now, whenever you read a theorem in mathematics, the very first question because each theorem has some assumptions and has some conclusions. So the very first question you have to ask yourself is that, what about if you remove some assumptions of the theorem? Because normally, if there is an assumption mentioned in the theorem, the assumption is necessary and is required, meaning that if we remove that assumption, the statement is not valid anymore. That's the normal situation in mathematics. But you could think about it, you could ask yourself, why do we need each assumption. What about if I remove one of them or remove two of them? Why the theorem will not be valid anymore? So in this case, my question is, can we, or if we remove the assumption of continuity of F, continuity of F at L is the statement still valid? Normally the answer is no, because if the assumption was not necessary, but mathematicians would have already removed it. So if you want to say no, or if you want to show something is false in mathematics, you know that we need a counter example. So you know that to prove a statement in mathematics, we have to prove in general. But if you want to prove something or show something is false, we need one counter example that has the assumptions, but not the conclusion. So the answer is no, i.e. If limit g of x as x approaches to equals L, then we cannot conclude that limit f of g of x as x approaches to A is equal to f of L, right? See, if limit g is L, and if f is continuous at L, then yes, we can say limit f of g of x is f of L. But if we remove the second condition and we only keep the assumption that limit g is L, then we cannot conclude that limit f of g of x is equal to f of L. So to show that this is true, that in other words, we cannot conclude this, we need a counter example. So what functions, f and g, do you think we can use that, you know, what functions f and g we can use that limit g is L, but limit f of g of x is not f of L? So here's a counterexample at g of x equals x at x equals 0. So then what can we say? We can say that limit g of x as x approaches to 0, of course, is equal to 0, which is our L value. And let f of x equals, let's say 1 if x bigger than equal to 0, and minus 1 if x less than 0. Then limit f of g of x as x approaches to 0. Well, g of x is x itself, so this is same as limit f of x as x approaches to 0. And this limit, of course, does not exist, right? Because the right limit and left limit will have different values, which is not same as minus 1, which is the left limit. Thus, we can say that the limit f of g of x as x approaches to 0 is not f of g of 0, which is 1. F of g of 0 is 1, but limit f of g of x as x approaches 0 is not f of g of 0, because this limit does not exist, but f of g of 0 is 1. Okay, so limit g of x has some L value, but f of x is not continuous at L, so f of x is not continuous at 0. So this causes limit f of g of x at 0 not to exist. So that means this condition of continuity at L is really important, and we really need to have it. Let's look at next example. Find all points of discontinuity for f of x equals sine x squared plus x over cos 2x on interval, let's say 0 to 2 pi. So here f of x is the division of one function by another function. So let's analyze numerator and denominator. So for sine x squared plus x, so this is composition of let's say, for example, g1 of x equals sine x and g2 of x equals x squared plus x. And both functions, both g1 and g2, are continuous everywhere. Continuous everywhere, so that means g1 of g2 of x also continuous everywhere. G1 is continuous everywhere, G2 is continuous everywhere, so G1 or G2 also continuous everywhere, because we already know, right, that if G2 of x is continuous at C and G1 is continuous at G1 of C, if G2 is continuous at C and G1 is continuous at G2 of C, then G1 or G2 will be continuous at C. We saw that this as a theorem. So if G1 and G2 both are continuous everywhere, so G1 or G2 will be also continuous everywhere. What about for cos 2x? So similarly, cos 2x is equal to composition of, let's say, for example, h1 of h2 of x, where h1 of x is cos x, h2 of x is 2x. So that means h1 of h2 of x. And again, we can similarly say that, h1 of x continuous everywhere. Are both continuous everywhere. So that means h1 of h2 of x also continuous everywhere. Right? So we have two functions which are continuous everywhere, and we are dividing them. So we had a theorem last time that said division of one function by another one is continuous as long as both functions are continuous and denominator is non-zero. So we just need to make sure that the denominator is non-zero. Of course, if denominator is 0, then that point will not be in the domain of the function, and therefore, of course, not continuous there. But if denominator is non-zero, then we have one continuous function divided by another continuous function, which will be continuous according to the theorem we saw last time. So we saw that the division of one continuous function by another continuous function is continuous if denominator is not equal to 0. So we can say that sine x squared plus x divided by cos 2x is continuous at every x equals c except the points at which cos 2x equals 0. And we are interested, so cos 2x equals 0, of course, has infinitely many solutions on the set of real numbers. But we are only interested on the interval 0 to 2 pi. So on the interval 0 to 2 pi, so thus the only points of discontinuity for f of x on 0 to 2 pi are so are which points? So we want cos 2x to be 0, so that means 2x could be equal to pi over 2 or 3 pi over 2 or 5 pi over 2 or 7 pi over 2 or 9 pi over 2. So still, see, 9 pi over 2 is more than 2 pi, but this is the value of 2x. If 2x is 9 pi over 2, x will be 9 pi over 4. Yeah, sorry. So 9 pi over 4 is also more than 2 pi. So we should not, we should stop at 7 pi over 2. See, up to this point, 7 pi over 2 is also more than 2 pi, but when you divide by 2, because this is 2x, when you divide by 2, 7 pi over 4 will be less than 2 pi. So up to here is still acceptable. But 9 pi over 2 divided by 2, even when you divide by 2, becomes 9 pi over 4, which is still more than 2 pi. So this one we should not include. So then x is equal to pi over 4 or 3 pi over 4 or 5 pi over 4 or 7 pi over 4. So these are the points of discontinuity for f of x. The points of discontinuity for f of x on the interval 0 to 2 pi. Okay, so that's about the continuity of composition of two functions. Now let's look at continuity of inverse of a function. Continuity of inverse of a function. So the theorem says let f of x be an invertible function which is continuous at every point on its domain on its domain. Then F inverse is also a continuous function on its domain, i.e. on the range of F. So let me give you a recall here about invertible functions. First of all, F is invertible if F is 1-to-1, if and only if, actually. If and only if F is 1-to-1. Second remark is domain of F is same as range of F inverse, and range of F inverse, range of F is same as domain of F inverse. And the third remark I want to say is that every increasing function is 1-to-1, and every decreasing function is 1-to-1. Okay, so when we say, so first of all, remember that F inverse, the main job of F inverse is that it interchanges the input with output. So every input becomes output and every output becomes input. Now, if F is a continuous function on the domain, on its domain, on the domain of F, then F inverse is also continuous on its own domain, on the domain of F inverse, which is range of F. And these are some quick remarks about invertible functions. And well, of course, you know that in the whole first lecture, I gave a review of pre-calculus, including these remarks. So I don't want to spend more time, but about the reminder, but you know, these are just a quick reminder about invertible function. So let's look at an example and show that f of x equals x cubed plus x is invertible and also, let's say, can we say that f inverse is continuous on minus infinity to infinity? Okay, so first of all, why is this function invertible? So invertible means 1-to-1, according to the first remark. And well, 1-to-1, to show that the function is 1-to-1, of course, you can use the original definition of 1-to-1, which says if f of a is equal to f of b, then a is equal to b for every points a and b in the domain of f. So that's one way to show that a function is 1-to-1, but you can also use these properties or theorems that, for example, if you have an increasing function, then the function will be automatically 1-to-1, or if you have a decreasing function, it will be automatically 1-to-1. Now, this function x cubed plus x is an increasing function, and therefore it will be 1-to-1. How can we show that it's increasing function? So to show that f of x is invertible, i.e. 1-to-1, we will show that it is an increasing function. Increasing function. To do this, let's start with a less than b. If a is less than b, then we can say that a cube is less than b cube, right? So increasing function means if a is less than b, then f of a is less than f of b. If a is less than b, we have to show that f of a is less than f of b. But what is f of a? F of a is a cube plus a, f of b is b cube plus b. So I first construct a cube and b cube. So if a is less than b, then a cube less than b cube. So if I add this inequality to it, add with this inequality, what do we get? We get a cube plus a less than b cube plus b. And f of a is a cube plus a, f of b is b cube plus b. So then we get f of a is less than f of b. This is valid for any points a and b in the domain of f, which is minus infinity to infinity. For any points a and b, if a is less than b, then we can say a cube less than b cube. Therefore, add with the original inequality, we get f of a less than f of b. And this means the function f of x is increasing as desired. Now, f is a polynomial, therefore it's continuous everywhere. Now, f is a polynomial, and hence continuous on minus infinity to infinity, which is same as r. Thus, by theorem above, f inverse is continuous on which set? Look at the theorem. Theorem was saying that if f is continuous on its domain, f inverse is continuous on its own domain, domain of f inverse, which is range of f. So f inverse is continuous on range of f, which is also minus infinity to infinity. And domain of f inverse, let me say this one, on domain of f inverse, which is same as range of f, which is same as minus infinity to infinity. Now, why can we say that range of f is minus infinity to infinity? So for the proof of a range of f equals minus infinity to infinity, see below. So I'm going to prove for you in a few minutes that range of f for this function is minus infinity to infinity. Once we prove that, we can say by the theorem, we can say that f inverse is continuous on minus infinity to infinity. And this is exactly what the question was asking us. It was saying that, can we say that f inverse is continuous on minus infinity to infinity? Yes, because f is continuous everywhere. So f inverse continuous on the range of f, and range of f we will see in a few minutes, that is minus infinity to infinity.